All right, so on 3.5, these are transformations of graphs. So 3.5, I may or may not make it through the entire notes because it's pretty straightforward. It kind of is repetitive, but we're going to kind of talk about as much as we can in 3.5 and go from there. So up first, our objectives. So our objectives are to graph functions using vertical and horizontal shifts. So slides across left and right. Talk about graph functions using stretching and shrinking. So we're going to be dilating our function. Okay. We're going to graph functions using reflection. So reflecting across the x-axis and the y-axis. And we're going to combine our transformations to make a total, like a full move, because no function is just in real world is just straightforward. Like you're never going to have a perfect linear or a perfect quadratic or a perfect anything or the parent function. Okay. The end game is that these are posted for you to write down on your bright space, okay? Because you're not going to have time to write all of this down right now in class, but I just want to make sure that we can all see it. So here we have our transformation rules for all of the functions. These are all of the rules, okay? So when you have a function and you are adding a value to the function, so you're not touching the x, you're adding a value to the function, that means that you are vertically translating your function up and down. Does that make sense? Okay. Which means that mathematically you are adding values to your y, but doing nothing to your x's. Okay. And the same goes for when you are subtracting that value. You are subtracting, which means that you're going to cause your function to go up and down. Okay. So you are subtracting values from your y, a said value from y. Next is our C transformation variable. Our C transformation variable is our horizontal translation, okay? Our horizontal translation, I like to tell you, think of this as your x's are liars, okay? Your x's are liars because it says plus C, but you're actually not going to the right. You're moving to the left, okay? So notice it says plus C. I'm actually going to the left, which means that I am subtracting from my x values, okay? This says f of x minus c. So if you see f of x minus c, it's a horizontal translation that's shifting your function to the right, which means that to your x values, you are adding c, okay? Your x's are liars. That's why they should be an x, okay? Get it? Okay? Life lesson in there for you, okay? All right, moving on to reflections. You have two types of reflections. You have over the x-axis or over the y-axis. If I'm reflecting over the x-axis, the negative is going to be the outside of my function. It is not going to be on my x. It's going to be outside of the function. And that's because I'm changing the output. I'm changing the outcome. I'm changing my y values. My y's are changing signs, okay? A negative means that you're changing the signs. Not that everything's going to become a negative, but if I'm a positive, I'm going to become a negative. If I'm a negative, I'm going to become a positive. And that's what's going to cause me to reflect over that axis, okay? All right, so negative on the outside is a reflection over the x-axis. A negative on the x on the inside is a reflection over the y-axis, okay? And therefore, my x values are the ones that are going to be changing the signs because I'm going across the y-axis. So I'm going from left to right, right to left. So I'm going across. All right, last but not least are what's called our dilations, okay? A and B describe our dilations. Your A is going to be your vertical dilation. And when we talk about dilations, we describe them as a stretch or a compression, okay? Sometimes you may hear reference as a shrink instead of a compression. It's just a shorter way of saying compress, right? I'm shrinking it down, all right? So for your vertical, think about this as you working out, right? Okay, this is how I think of vertical stretch. If my A is greater than 1, so I start going to the gym more, my function is going to get skinny. It's going to stretch out. Does that make sense? It's going to stretch. Okay, it's growing at a faster rate vertically. All right. Now, let's say I start cutting my gym time down, right? I'm not stopping completely, but I'm cutting my gym time down. There's a likelihood that my hips are going to get a little wider again, right? I'm going to start widening out. I'm going to be compressing vertically. Does that make sense? Okay. And so that is how your A is affected. Your A is manipulating your Y. It has changes on your Y, your output. So you would be multiplying those values by A. Okay. All right. Next is your B. Remember how we said X's are liars? Right? This looks like multiplication. It's not. It's division. Okay. X's are liars. Okay. This is division, not multiplication. All right. So when you have BX, what's taking place is the opposite. Okay. Do we all know what an accordion is? Yeah. Okay. When I apply more pressure to an accordion, it compresses, right? So when my B is greater than 1, I'm applying more compression to my accordion. Does that make sense? So it's compressing. Yes? So more pressure is compressing it, right? Less pressure is stretching it. So I increase the pressure, I'm compressing. That's a horizontal compression. Release less pressure is going to be a horizontal stretch. Compress, stretch, compress, stretch. And now I'm playing the accordion. Okay. That is how your horizontal dilation works. Okay. It is the opposite of the vertical. All right. So, how does that impact your variables, your input? That's your X is now being divided by said B value. And that's because you are compressing when you're applying more pressure. You're shrinking it in, right? You're giving it less window of time to grow. All right. Okay. So these are our overall full transformations, and this is all of what 3.5 is about. Okay. What we're going to do is look at it in parts, but this is the overall concept of 3.5, and this alone is posted on your bright space for you to write down later because we don't have time for every single person to write every single thing up here down. There's no way. Okay. All right. So let's look at it in pieces. So for some of your textbooks or other teachers, you may see instead of using C and D, they may use H and K. Okay. The reason why you may see H and K is because H and K, when it comes to a quadratic, has a unique representation. It represents the vertex of your quadratic. Okay. So you may see when referring to quadratics, it as H and K. That's because H, comma K is your vertex. All right. You're saying that I moved my vertex from 0, 0 to here, right? I went left or right one of these ways. Does that make sense? And your vertex is going to be the main point that shows that transformation. Okay. Your H is your horizontal, which is the X of your vertex, and your K is your vertical, which is the Y of your vertex. Okay. So again, that means that we are adding to the Y values for our K, and we are doing the opposite with our X's because X's are liars. All right. So vertical shifts, again, are going to cause your function to just simply go up and down. These rules apply to every single function. Every single function, these rules apply to, okay? It's going to cause your function to go up and down. So we're going to look at not a quadratic, but we're going to look at a square root to show you that this is going to happen regardless, all right? So starting off here, we have the function f of x equals the square root of x. To obtain the graph of h of x is the square root of x minus 2. This is going to be a vertical translation down 2. I know that it is down 2 because it says what? Negative 2. I know that it's vertical because it's away from the x. Does that make sense? That's how I know that it is vertical. All right. So for our square root function, we're going to use the parent function values. The parent function values for square root are 0, 4, 9, and it keeps going. We'll just stick to these, but 0, 4, 9. Okay. The square root of 0 is, remember, f of x equals the square root of x. Sorry, didn't write 2 there. Equals the square root of x. What is the square root of 0? 0. What is the square root of 4? 2. What is the square root of 9? 3, right? H of x is telling us that we're going to shift down 2 units. So h of x is saying that we're taking our square root function and we're shifting down 2 units, which means that I'm taking my current y values and subtracting 2 from each one of them. Does that make sense? So my current y value here is 0 minus 2 is now going to put it at negative 2. Does that make sense? Okay. I'm currently at 2. 2 minus 2 is now going to put me at 0. I'm currently at 3. 3 minus 2 is now going to put me at 1. Okay. A horizontal translation has no impact on your x's. Your x values are going to apply to each one of these. So we're going to look at it graphically. So I'm going to graph my first one, which was my original one. So I'm going to graph 0, 0. I'm going to graph 1, 2, 3, 4, 2. 5, 6, 7, 8, 9. 1, 2, 3. And 9, 3. And when I graph, pretend that that's like super curved. It's a curve. It's going like that. Okay? And literally all I'm doing is taking that and shifting it down 2 units. So now at 0, I'm now at -2. Now at 4, I'm at 0. Now at 3, I'm at 1. So do you see how all we did was shift it, translate it. Sorry for saying shift. We translated it down 2 units. So we did it mathematically and we did it graphically. Well, sorry. What is it called when you use a table? Numerically. We did it numerically and we did it graphically. Because mathematically is what we're doing all together. All right. How do you feel about a vertical translation? Okay. You have the table view, you have the graph view. Either way, just do it. All right. Would it be any different if I was going up? Nope. The only difference would be me adding 2. Okay. Questions about this? Nope. All right. Let's talk about horizontal shifts. So your horizontal shift, remember our x's are what? Okay. X's are. All right. So our x's work differently. When I see it, it says x minus h, I'm actually going to the right. Okay. That means I am adding to my x values, right? So we're add to x values. Okay. When we see that it says x plus h, we are shifting horizontally to the left, which means that we are subtracting from our x values. Okay. What we're going to see is a combined transformation of a vertical and a horizontal next. Okay. So it's going to be a combination of the two, which means that we have 2 things to do, right? We're going to have to move our x's and we're moving our y's, which essentially means that we're moving our vertex. Does that make sense? All right. Give y'all a minute to write that down. Or something. All right. Do we need a little more time to notate anything? Are we okay to go? Okay. I realize I need to add one more column to my table since I'm doing both of them. Perfect. Hopefully that's better. All right, here we go. So everyone should have a moment to write down. Here we are. So we have the graph. We're going to graph the function f of x equals x squared and h of x equals x minus 3 squared plus 2. And we're going to find the domain and range of h, the new one. Okay, so this is from the beginning of our unit where we talked about this is our parent function, right? F of x equals x squared is our parent function. The parent function values that we used were, I believe, -3, -2, -1, 0, 1, 2, and 3. Okay, That is the weirdest little box that I cannot, whatever reason, write in. Y'all see that too, right? It's just, there's a 3 there, okay? It's right there. It's going to have to be outside the box, okay? So for your original function, which is x squared, f of x equals x squared, all you're doing is squaring each one of your x's, right? So negative 3 squared is 9. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. I know, but it's just so weird. Found it. Okay. All right. So that's our parent function, our original one, right? So for the parent function, I'm going to do a quick little sketch of it. Is it going to be beautiful? I'm going to tell you it is. And then your sketch can just be just as beautiful because it's your notes and just. All right. There she is. So now we're going to look at our transformation. So our transformation now is we have x minus 3 squared plus 2. So the 3 and the 2 are the new pieces, correct? That 3 is affecting our x's, right? And our x's are what again? Evil. They're liars, right? So our new x's are actually, we're adding 3 to our original x's, right? So to all of our original x's, we're adding 3, okay? That plus 2, that's our outside. That's telling us what's happening to our outside, our output, right? Our y values. So to each one of our original y values, the h of x is going to be y plus 2. So whatever our original y values are, it's going to become y plus 2. Does that make sense? All right, so to each one of my x's, I'm adding 3. So negative 3 plus 3 is going to put me now at 0, right? Are you with me? Okay. Negative 2 plus 3, I'm not going to, hopefully we'll see that it's a pattern, and then I can stop writing it out. Do we see the pattern? Okay, so now we're at 0, 1, 2, 3, 4, 5, and 6. All right, that's our horizontal translation. Now we're going to do our vertical translation. Your vertical translation is saying that to all of your original x values, you're now going to add 2 to them, correct? So to my original x, my y values, I'm sorry, we're going to add 2. So that's 9 plus 2, which is now where? 11. So we have 4 plus 2, which is now going to put us at 6. We have 1 plus 2, which now puts us at 3. We have 0 plus 2, which now puts us at 2. And then these values are going to repeat because our values are the same. So we're now at 3, 6, and 11. So our new function point values are going to be at, we're at 0, 11, 1, 6, 2, 3, 3, 2, 4, 3, 5, 6, and 6, 11. Those are the new homes after my transformation. Okay, so we're at 0. I'm going to go up to 9, 10, 11 is going to be a little bit off the board, right, for me. And then we're at 1, 6, 1, 2, 3, 4, 5, 6. We're at 2, 3, 1, 2, 3. We are at 3, 2, 1, 2. We are at 4, 3. We're at 5, 6. And we're again off the board at 11. Connect the dots. Pretend that that is the best parabola you've ever seen. And can you see that I shifted my parent function 2 units to the right and 3 units up? Okay. When you make these transformations, your domain isn't changing, but your range does change, right? So it says now what is the range of h? So the range of h of x equals what now? What is my lowest value now? What is my lowest y value? 2. So now I go from 2 to infinity. So instead of 0 to infinity, I now go to 2 to infinity. So those are our horizontal and vertical translations combined. Questions about either one? No? Okay. Up next is going to be our compressions and stretches. And some textbooks you may, or in previous classes, they may have referred to this just as dilations. Okay. Dilations is just combining compressions and stretches. You also may see that compressions may be called a shrink. Okay. So we're now talking about dilation. So geometry words. Your vertical compression or stretch is when you have a coefficient outside of your function that is now going to change it. So that's when you have that a on the outside that we talked about. If your a is between 0 and 1, then it's a vertical compression. If your a is greater than 1, it's going to be vertical stretch. Altogether, regardless of what your a is, that means you're taking your a and multiplying it by your original y value. So whatever your original y values are, you're multiplying them all by that a value. Make sense? Okay, let's talk about our horizontal. Horizontal, remember our x's are what again? Liars. And this got disheveled, and I don't know why. But your horizontal is going to be the opposite. It's going to be a division. So for your horizontal, even though you can't really see it, what it means is you're taking your x values and dividing them by whatever the a value or b value or whatever you want to call it, but the coefficient that's with x. That's what you're doing to all of the values in your table. Okay? Because x's are liars. It looks like a multiplication, but it's actually division. Okay? You're essentially multiplying by the reciprocal is what it is. So that's what that 1 over a means. So when that 1 over a, this is what it's telling you to do, is to multiply this, which is the reciprocal. Pretend there's a C there. All right. Let's just dive in. So on this one, my variable, my coefficient is outside. It's away from the x. Do we see that? Because it's away from the x, I know that this is a vertical. Does that make sense? So it's a vertical compression or shrink. Which one? I'm working out more, so I am stretching out, right? So this 3 is on the outside, which lets us know that it is a vertical. And it's going to be a vertical stretch by, I can't write. Vertical stretch by a factor of 3. Factor of 3. Which means my y values are changing, not my x values. Does that make sense? So I'm going to go ahead and write down all of my x values, and my x values aren't changing. So I intentionally gave you one that had pi because it doesn't matter, right? The pi's aren't going to change anything. So my x values are negative pi. I have negative pi over 2. I have 0. I have positive pi over 2. I have pi. And I have 3 pi over 2. Oh my gosh. The box has moved up. Y'all gotta admit, that's a little weird that there's a space on an imaginary screen that I can't write in. It was not like this at all last year, so I have no earthly idea. It's so weird. Forget about 3 pi over 2 right now, because I can't write it. So 1, 2, 3, 4, 5, and 3 pi over 2 is there. So my original f of x, my values are currently 0, 2, 0, negative 2, and 0. And then we're at 2 again. I really wish I knew why it's doing this. 3 pi over 2, comma 2. I'm just going to write them together because I can't write them separately. All right, so that's the x and the y. The transformation says that I am multiplying all of my y's by 3. So my transformation is I'm taking all of my y's and multiplying them by 3. So my new y's are going to be 3 times 0, which is 0. 3 times 2, which is 6. 3 times 0, which is 0. 3 times negative 2, which is negative 6. 3 times 0, which is 0. And then 3 times 2, which equals 6. So all of my points are being stretched except the zeros. Notice that the zeros did not move. Make sense? So this value is now going all the way up here. This value is now going all the way off the board, and I can't do anything about it. And this value is now going all the way up here. So it's literally vertically. Pretend that it went down there. Stretching. Does that make sense? And that is a vertical stretch. Okay? And the vertical stretch, again, is impacting the y's. All right? Your horizontal. So your horizontal stretch, it means that you're changing your x's, right? So for this one, it's with the x. So I know that this is a horizontal and it's greater than 2. So I'm lessening my, I am applying more pressure, which is shrinking it. X's are liars. So it's a horizontal, and this is going to be a compression because I'm applying more pressure, right? So it's a horizontal compression by a factor of 1/2 because that's the reciprocal of 2. Because I'm not multiplying by 2, I'm doing what with the 2? Dividing, because our x's are liars. So we're not multiplying the x's by 2. We are dividing the x's by 2. So that's why it's a compression by a factor of 1/2. Okay, so my original x's that we had were negative pi. We have negative pi over 2. We have 0. We have positive pi over 2. We have pi. And we have 3 pi over 2 who won't be our friend. Okay, so my new x's are going to be x's divided by 2. Okay, so now this is going to become negative pi over 2. This is going to become negative pi over 4. This is still going to be 0. This is still going to, I'm sorry, yeah, this is still going to be 0. This is going to become positive pi over 4. This is going to become positive pi over 2. And then this one is going to become 3 pi over 4. But my y's are staying the same because there's no impact or change on the y. So your y's are still going to be 0. It's still going to be 2. Still going to be 0. Still going to be negative 2. Still going to be 0. And still going to be at positive 2. But these are your new values, and these will be the points that you would plot to create your compressed function.